Example 8.2, an electron has a velocity of 52.2 kilometers per second at 51.2 degrees relative to the magnetic field of 60 microtesla along the x-axis. A, draw a complete picture of the trajectory of the electron. Calculate the radius of the helical path, its frequency, and the pitch of that path. So let's start by drawing a sketch. So let's sketch a diagram of this situation. It tells us that the velocity is 60 degrees relative to the x-axis, or 51.2 degrees relative to the x-axis. Note that it's not telling us about the direction of the magnetic field. Well, it does tell us about the direction of the magnetic field, but it doesn't give us all the details about the velocity. Is it velocity in the x and the z? Is it in the y and the x? Or whatever here. So we're going to have to make some assumptions. So I'm going to say that because of the lack of information, the velocity is in the xz plane. I could have picked the xy plane just as well. And we need to pick a coordinate system that will be useful. So I'm thinking I want my motion to be in the xz plane. So right away, I'm going to pick my axes. So let's say that I'm going to pick this to be my x. And let's see, can I pick in, I'm going to pick my z in this direction. So now using my right hand rule, I can then see here is that if I have x, y, let's make sure that I get that. So I get x, y, and z. So then that tells me that into the plane is then going to be my positive y-axis. Okay, so that's where I'm at. So again, it's arbitrary how I pick my coordinate system, but this seems to be a useful. So why is this useful? The magnetic field is in the x direction. So let's draw that. So I see I have a field. And that's going to be my magnetic field. And they tell us that this magnetic field is equal to 60 microteslas in the x direction. So then my velocity is going to be 60 degrees or 51.2 degrees relative to the z-axis. So that means I have to have a component that's going to be in this direction, which I'll call v parallel. And then, of course, this is the angle that we're talking about. And this angle here is 51.2 degrees, even though I keep saying that this angle is 60 degrees, it's not. And then I have another component that's going to be V perpendicular. So you could see that V parallel has to have, it's on the adjacent side. So that means here this has to be V cosine of theta. this has to be v sine of theta. So now I have my velocity component. So then this guy here is then going to be in the x direction. This is going to be in the z direction. So now I have my velocity and magnetic field components. So what do I expect to happen? I need to look at the right-hand rule. So now from this picture here, I want to get in and try to draw this nice and clean. So what am I seeing? The only thing that's going to cause circular motion is the perpendicular component. So if I look at the perpendicular component, I see here that I have a magnetic field in this direction. I have my velocity that's pointed in this direction. So then what direction is my magnetic force? Since this is an electron, I'm going to have to use my left-hand rule. And if I use my left-hand rule, it tells me that the magnetic force is pointing outwards for a negative charge. So now if I start to look at this and what does this actually look like, I have my magnetic field lines. And so I know that the magnetic force is popping up right here and the charge is going up. Okay, so this charge is going up. So what this is trying to make it do here is it's going to make it wrap around the magnetic field lines from the back view. I'll show you in here in a minute. Let me draw this out. So then I'm going to see my V perpendicular. And remember, I still have a velocity that's parallel here. So then if I look at that magnetic field, how this charge is going to wrap, it's going to rotate like this, and then it's going to come around, and it's moving in that type of path right there. And what's making it helical is again that perpendicular component that's looking like this. So now that I have the setup, I want to go in and start calculating values. To calculate the radius, start with Newton's second law and look at circular motion. So that means that if I have a magnetic force, this will then be mass times the centripetal acceleration, which is mass times v perpendicular squared divided by r, and that has to be q v perpendicular times b. So if I isolate the radius in this case, then I have my radius, which will then be the mass of the electron, the velocity perpendicular, times E times B. There's a lot of numbers here. But let's put in all the details first. Now note that V perpendicular is associated with the sign. So this should really be ME times the velocity times the sine of 51.2 degrees divided by the charge and the magnetic field. So there's a lot of values. you're going to have to look up the mass of the electron. The mass of the electron is 10 to the minus 31 kilograms. We already know what the charge of the electron is, which is 1.60 times 10 to the minus 19 coulombs. They give us what the speed was. The speed was 52.2 times 10 to the 3 meters per second, because it's 52.2 kilometers. And then they tell us about the magnetic field strength. They told us that the magnetic field strength was 60 micro Teslas. So I need to put those values in. So if I put these values in, I'm going to find that I'm going to get R, which will then be 9.11 times 10 to the minus 31 kilograms, times my speed, which will be 52.2 times 10 to the 3 meters per second, times the sine of 51.2 degrees. This is going to get divided by the charge, which will then be 1.60 times 10 to the minus 19 coulombs, times my magnetic field, which would be 60 microteslas. And so if I compute this number, assuming I did not make any errors in my number calculations, I get 3.80 times 10 to the minus 3 meters. A more convenient factor might be in millimeters. So you could see here that this is a tiny radius, and that's what we end up with right here. So now that I have the radius, I can go calculate the period. So the period, cyclotron period, or I could have said frequency just as well, right? Cyclotron period or frequency is, I think the easiest way to calculate is just look at the definition of the speed. So if I look at the definition of the speed, it should be distance divided by the time, but that time is the repeat distance, so it's moving in a circle, so it has to have its circumference divided by the cyclotron period. So now if I go calculate the frequency, that frequency is then going to be 1 over the period, and then just manipulating this equation, I'm going to get 2 pi r, and then I'm going to get v perpendicular, oops, not v perpendicular, but v sine of 51.2 degrees. Again, putting in my values, I'm then going to have 2 pi times 3.80 times 10 to the minus 3 meters. Up here, I'm going to get 5.52.2 times 10 to the 3 meters per second times the sine of 51.2. And when I compute that number, I get, I'm going to bring this down, I'm going to get 1.67 times 10 to the 6 hertz. And that's my cyclotron frequency. So finally, the last parameter is the pitch. The pitch x pitch is the repeat distance of the trajectory. So if I look at my magnetic field, and I know that this electron is wrapping itself around these field lines, we are trying to calculate this distance from here to here. But what we know here is that this guy is moving horizontally at V parallel. So when I go to calculate that distance here, we then say that X pitch has to be how fast is it moving parallel, and then this here, that time, is going to be this in the cyclotron period, or I can write V cosine of 51.2 divided by the cyclotron frequency. So if I put in these values here, I'm going to get 5.2, 52.2 times 10 to the 3 meters per second. I have cosine, not sine, and then my frequency is 1.67 times 10 to the 6 hertz. And so when I compute this number, I get a numerical value of 19.1 times 10 to the minus 3 meters, which is also 19.1 millimeters. And this guy is X of pitch. So what does this cycle look like? One way to get a sense of what this looks like is that to get a better description of the motion, calculate the ratio X pitch to the radius. So if I look at X pitch to the radius, in this case, we have 19.1 divided by 3.80, and that's about a factor of 5. So that means the pitch is 5 times longer than the radius. So how do I draw something like this? So I'm going to imagine that I have my magnetic field like this, and I'm only going to draw a couple of lines here. So then if I look at the motion, it's got to look something like this. It's got to have a really long motion as it wraps all the way around these magnetic fields. So when I'm looking at this, we can see here is that this from here to here is X pitch. And then from here to here, which is hard to imagine here, that might be the radius, R. So it looks like I drew it too long, but is that 5 times? It looks like it might be a little bit too long, but that's a good description of the cyclotron frequency.